Okay, hi everyone. Thanks for being here. My name's Arno. I'm a software engineer on the RabbitMQ team at VMware. And today I will be speaking about streams in RabbitMQ, how they work, what they are good for, and how you can use them in your Spring applications. Before we start, I'll let you have a look at this disclaimer, legal stuff. Let's take a few seconds to read it. Okay, thank you. And the agenda. There will be an introduction, an overview of RabbitMQ streams, how they work, why we introduced them in RabbitMQ, and how they can be used in your Java application and especially in your Spring applications. So streams. We introduced streams in RabbitMQ a couple of years ago. Before that, we had only queues in RabbitMQ. And streams are very different from queues. Stream models an append-only log, where you just accumulate messages. And streams are always persistent and replicated. And a big difference between streams and queues is that streams have non-destructive consumer semantics. It means that when you read messages, when you consume messages from streams, you don't remove them from the stream. They are still in the stream. And you can interact with streams from your applications using the supported protocols in RabbitMQ. That means MQTT, AMQP, STOMP. And we also introduced a new specific protocol just for streams. What they are good for? Streams are good for large fan-outs when you have several applications that need to read the same messages but do different stuff with those messages, different processing. You can also go back in time with streams. So you have this replay time-traveling feature. You can attach to consume from a stream anywhere, basically, in the stream. They are also fast, much faster than queues. We'll see numbers later in the presentation. And streams are also good for large logs. It means that you can keep a large history into your streams. Whereas usually with queues, you want to keep them empty. So why streams in RabbitMQ? You can do a bunch of stuff with queues, but they have limitations by nature. So streams are there to complement queues. You can just do different stuff with streams. So streams are really there to complement queues. And they help to unlock use cases that could have been difficult to implement just with queues. New use cases and hard to implement just with queues and also awkward to implement and scale out. So let's see how queues work, and this will help us to understand how our streams are different from these queues. So here we have a simple queue with a couple of messages in it, and we have a consuming application. The broker will dispatch one message to the application, and the application will start processing this message. And at this point, the message is in two places, in a way. So it's still on the broker side, and it's being processed. And when the application is done with the processing, it acknowledges the message, and that at this point, the broker removes the message from the queue. So that's what we call a destructive consuming, because when you read, you actually remove. It's a reading operation which is not just read-only. And another use case with queues, which can be awkward to implement, fan-outs. So it means that in this case, you want to have several applications doing different things with the same messages. Let's start with one application with one queue. So in RabbitMQ, you publish to exchanges. You don't publish directly to a queue. Thanks to that, you can have a routing logic on the broker side. So you publish to the exchange, and the message will end up in a queue where your application can do its processing. Imagine that you want to plug another application that will read the same messages but do something else with these messages. You cannot just plug your application in the first queue because the applications will compete with each other. They're going to steal messages from each other. So you create another queue, bind it to the exchange, and you end up with a copy of your message. And you have your different application independently. And same thing if you want to have a third kind of processing. So it works. Fan-outs work with queues, but as you can see, it can be a bit awkward. Queues are cheap in RabbitMQ, but not that much, and there must be a better way to use your resources. So streams. A stream is just a log. It models an append-only log. You can see this log as this kind of pipe, just like a queue, where we accumulate messages. So oldest messages on the left and latest messages on the right. Each message has an offset. So this is this number. It's like an index, like the index in an array, but that's enough for what we need. But it's not exactly an index. Anyway, that's some kind of ID in the stream. And that's it. Very simple data structure, and we just accumulate messages. When you want to consume, you can start from the beginning and read all the way through your stream. You can attach also at the end, even at the very end when there's no messages yet and you're going to see only new messages. And you can attach anywhere in the stream, for example, at some point where your application stopped, and when it restarts, it can resume where it left off. And you can have any number of consumers at the same time on the same stream. They don't compete with each other. You can also have the same application reading and rereading a stream. For example, a batch application running every day is going to start one day, do its processing, build some views, stops. The next day, it will start again from the beginning, compute the views, but with the additional data from the day before. And if you are familiar with RabbitMQ, queues in RabbitMQ can be on one node of the cluster, can be in memory, can be persistent, can be replicated. So we have many options, but streams are a bit more opinionated. They are always persistent and replicated. And we have this leader and follower mechanism whereby you have a leader for a leader process for your stream, and it accepts writes, but it's the only one that can accept writes, so new messages. And then followers replicate the data from the leader. So just imagine a stream as a small cluster within your RabbitMQ cluster. It's also possible for the application to implement data locality. Imagine that you want to publish to a stream. You can find out about the topology of the stream and from your application and locate the node that hosts the leader of the stream you want to publish to. So you connect to this node and you avoid network hops between the node of the cluster. And for consumers, same thing. You can find out about followers, where they are in your cluster, and connect to these followers. This way you offload the leader of the stream, which is busy handling the writes. Okay, so we can optimize this way, and this is what we do in the client libraries that we wrote for streams. But don't think that you're going to end up with one node of your RabbitMQ cluster with all the leaders, or some kind of stream leader, a node which is the stream leader for all the streams. Streams, again, are some kind of small clusters inside the RabbitMQ cluster, and we try to distribute the stream leaders on the cluster. So this way, if you lose a node because of an upgrade, you won't move all your leaders, all the stream leaders, from one node to the other. So on this diagram, you have three streams, and they have leaders, a respective leader, and followers. And as you can see, the leaders are spread across the nodes. How can we work against streams? Streams are still just a resource inside RabbitMQ. You can have your classic queue. A classic queue is just a queue on one node, which is not replicated. You can have also quorum queues. This is the last generation of persistent and replicated queues in RabbitMQ. And you can just create your stream. It's seen as a regular queue, actually, except the semantics are very different from a queue. So you create your stream, bind it to your exchange, and then you can use the exact same libraries as before, AMQP libraries, to interact with the stream. Some numbers. So we did some simple benchmarks with between a quorum queue and a stream. Why did we choose a quorum queue? Because it's also persistent and replicated. So on this diagram, we have the throughput, the number of messages per second. So it's it's 39,000 with the quorum queue, and the stream is a bit faster at 64,000. It doesn't mean that the stream is it's better. It's just that here it reflects that a stream is simpler than a queue by its semantics. You don't have to deal in a stream. You don't have to deal with acknowledgement, requeuing, removing data from the structure. So the stream is just a bit faster, which is quite normal, actually. So it doesn't mean that you should stop using quorum queues. Again, there are very different data structures, so you are going to use one or the other depending on the use case. But at least here we have numbers. This is when we use AMQP, so the historical protocol supported in RabbitMQ. But I mentioned at the beginning that we introduced a new protocol for streams in RabbitMQ. And if we compare these numbers with the same stream, but using the stream protocol, as you can see, it's much faster. So we have the same numbers on the left, so it's 39,000, 64,000 with AMQP, but it's over 1 million messages per second with stream using the stream protocol. So much faster. We optimize the protocol for throughput, and also all stream, the stream structure itself on the file system is actually very optimized as well. So what is it about this new stream protocol? So it's fast, at least faster than with AMQP. It's available as a plugin in the core distribution of RabbitMQ. You have streams inside RabbitMQ core since RabbitMQ 3.9. They are there, you can create them, use them with AMQP or any other protocol. But if you want to use the Stream protocol, you need to enable the Stream plugin, and it will start a listener where you can connect your application to. It's all integrated into the management infrastructure in RabbitMQ. So the management web UI, the REST API, CLI as well. So you have commands to list your Stream connections, your publishers, your consumers. So it's a first-class citizen into the RabbitMQ infrastructure. So how do we use streams with the Stream protocol? We interact with streams directly. So if you publish to a stream, you actually publish to the stream, not to an exchange, like with AMQP. So there's no routing available on the broker side. And for consuming, you just attach to the stream. It's all interoperable. It means that you can have different applications from using different programming languages with different protocols, and they can all work against the same stream. So publish to the stream and see the messages from the other clients. So here we have an application using the MQP protocol. At the top, it can send messages to the stream, and the application at the bottom will see those messages, even if it's using the Stream protocol. Okay, we have conversion rules going on into the broker for all the protocols we support. So it means MQP, MQTT, Stomp, and also the Stream message format. So let's take an example of what you can do. This is maybe what you already have in your system. So no stream yet. That's a system where you have publishers publishing to an exchange, and the messages get routed depending on their location using what we call a routing key. So you have a queue for each region of the world, so Americas, EMEA, APAC, and depending on the routing key of your message, it will end up in a dedicated queue to do where a dedicated application will do the processing for the region. So imagine you want to try out streams, but without changing much in your application, just to experiment. You can create your stream to do, for example, worldwide analytics. In this case, we create the stream, we bind it to the exchange using this specific binding queue, a wildcard. So it means that when you have a message coming in, it can be for Americas, so it will go to the Americas queue, but it will also be routed to the stream because of the wildcard. So you end up with the stream, in the stream with all the messages from all around the world. And you plug your application using the Stream protocol, and this way you can compute worldwide analytics. So as you can see, not much to change in your application, very easy to test. Okay, about the guarantees that we provide in streams. So we have at least one semantics. It means that you don't lose messages thanks to a publish confirm mechanism. You have also on the publishing side message deduplication. If an application happens to publish a duplicate message, it can be filtered out by the broker automatically. There's also flow control for the consumers. It means that consumers can tell when they're ready to get more messages, okay, to avoid overwhelming them. And other features, I was mentioning this offset at the beginning of the presentation. It can be used to attach to a given point, but you can also use a timestamp you can attach at a given point in time of the stream, this day or this hour. We have, remember, non-destructive consuming semantics, so it means that a stream can grow indefinitely. At some point, we may need to truncate them. So it's possible thanks to retention policies based on age or size. When the policy kicks in, the beginning of the stream can be truncated to avoid overflowing the disks. There's also server-side offset tracking. This is, again, for consumers when a consumer can store the offset of the last message it processed. This way, when it restarts, it can resume where it left off. So this is built inside the server, but you can use any data store. You don't have to use it. It's just that you don't have to maintain an external data store, but you can still use a relational database if you want to store your offset at some point. And there's also secure communication between client and server, so TLS, just support for TLS. Okay, that's it for the basics of streams. So they've been there for a couple of years now. So we fixed stuff, we made them more reliable, robust, but we also introduced a couple of major features. One of them is single active consumer for streams. It brings exclusivity for your consumers and also continuity of service. Let's see how it works. So you imagine that you have a consuming application and you want to be on all the time. If the application crashes, you would like it to keep running in a way. If you just start several instances of the same application, this is a stream, so the application will just do the same and you're going to end up with duplicate processing. So what you can do is say that your application instances belong to a same group just by an ID. And this way, only one consumer at a time will be active. So you start your instances, the first one will be the active one and will get the messages. The other instances will just stay idle. And when the active application, the active consumer crashes or stops for some reason, the broker will just take the next in line and start dispatching messages to it. So you don't have much to do on your side. You just need some kind of application controller to start your instances, but you don't have to coordinate them.
In this case, will the new active one reread the old messages, or will it just get new messages?
So the question is basically where the new active one will start. It will, if you use if you use offset tracking, it's going to restart where the previous one, the active one, left off. Okay. And another feature is superstreams. So superstreams are a way to scale out if you feel you reach the limit of one single stream for your application. You can scale out by using superstreams. It's a partitioning solution. A superstream is just a logical entity that your application sees. Internally, it's actually implemented as individual streams, which are the partitions of the superstream. And there's, when you publish, there's client-side routing to route your messages to a given partition. And depending, if you do your routing in a consistent way, you can have, you can maintain order among the same partition. the publishing order. So for example, if you use a customer ID for the routing key in your, when you publish to a superstream, you can hash this, this customer ID, and all the messages for this given customer ID will end up in the same partition. Okay, and when you read them, when you read your messages, you can make sure that only one consumer at a time will see the messages for this customer. Superstreams build on top so streams and also single active consumer. So that's a design choice. We started with streams, so that's some kind of primitive. And then we added features on top of them. So if you want continuity of service, exclusivity, you have single active consumer for a single stream. And if you want to scale out, you can have super streams. But you don't have to start with a partitioning solution from the beginning. Okay? We chose to avoid that some technical details like partition leaks leak all over the place. So for simple stuff, you have just a single stream, which is quite fast already, for example. So how do you code against these streams? We have the Stream Java client. We support other programming languages, but I'm going to focus on the Stream Java client because I guess most of you are programming against Spring, so Java. The Stream Java client is quite simple to use. You start with an environment instance, which is usually there's only one instance per application, and from it you can create a producer. With the producer, you just have to specify the stream you want to publish to, and that's it. You end up with your producer instance. If you want to publish, you can create a complex message. A message is usually made of a payload, binary payload, but also headers, predefined headers. It's with complex types. And then you can send your message using the send method. So the message and a callback, which is asynchronous, which is the confirmation from the broker that your message has been taken into account, that is replicated on at least a quorum of nodes. And that's it. So underneath, the client will handles all the details of the protocol. It's all hidden for the application developer. For consuming something, you start from the environment. You specify the stream you want to consume from. By default, you consume from the end, the very end of the stream. So in this case, I chose to start from the beginning, and you provide the callback to process a message. And again, that's it. You don't have much else to do. So we try to make the API as simple as possible for the application developer and avoid having to know a lot about the protocol. And how does it work with Spring? It starts with Spring MQP. You have Spring MQP, you have Spring Rabbit, the Spring Rabbit module inside it, and it builds on top the Stream Java client. For publishing, there's the usual template which is used in the Spring ecosystem when you want for data access. This is for publishing, and for consuming, you have the Rabbit listener annotation to annotate your POJOs and make them message-driven. So why do you want to use Spring MQP? What does it do for you? The Stream Java client is quite simple to use already, but it's still an API, and maybe you don't want to rely on some API, you want to decouple your business code as much as possible from the infrastructure, and the Stream Java client streams are the infrastructure in this case. So with Spring MQP, you don't have to use the message API, the producer API that we just seen in the Stream Java client. You can just use POJOs. You can make Spring MQP wrap and unwrap the messages and just extract the, for example, the body as a string or even as a domain object using Spring's message converters. So basically, thanks to Spring MQP in this case, you can stick to the POJO programming model that we like in Spring. You are also in a Spring application context, so it means you can use dependency injection, you can use AOP. Basically, you are inside the Spring world when you are using Spring MQP. There's also a couple of auto-configuration classes in Spring Boot, so you can really easily start your, you don't have to do much setup when you want to do some RabbitMQ streams in your Spring Boot application. You can also have the actuator, micrometer matrix, and so on, all of this available very easily. It's inside Spring MQP, but it's using the Stream protocol in use. It's using the Stream protocol, sorry, not the MQP protocol. Just some samples. So with the template for publishing, you provide this is configuration only for the first line. You provide the environment and the stream you want to publish to. And then you can use, for example, convert and send to a message to the stream. In this example, the content is just a string, so it's going to be wrapped into the message API, but your code just depends on the string type, a simple type. And you get you get a future in this case for the asynchronous publish confirm. Okay, same thing. You stick to simple types or JDK types. You don't have to use the Stream Java client API. For listening, you have the annotation, the Rabbit listener annotation. You annotate your POJO, and that's it. It becomes a message-driven POJO, and you get messages to it. In this case, again, you just depend on a string. So you imagine that Spring MQP will unwrap the body from the message and pass it into your method. This makes your code, your business code, very decoupled from the infrastructure, very easy to test, and very easy actually to switch to another solution for messaging. You can configure your listeners. Here, this is the definition of the listener container factory. The interesting line is the one with the comment at the end. This is where you can actually customize your consumer and say, for example, for this consumer, I want to start at the beginning of the stream. But again, this is just configuration. This is not your application code. You can go further because there's also integration into other places of the Spring ecosystem. There's also support in Spring integration with a couple of adapters to consume, to publish to streams. So this way you can embed RabbitMQ streams into your Spring integration flows, implement your patterns, the enterprise integration patterns that you already support in your applications. And there's also support in Spring Cloud Stream. So Spring Cloud Stream is a framework for to implement microservice applications and kind of connect to them, them to each other. And you can use, in this case, thanks to a Spring Cloud Stream binder for RabbitMQ streams, you can connect your microservices with RabbitMQ streams. This way you can benefit from this transport layer advantages, so the throughput is much faster than with queues, and also the replay mechanism. You can replay all your messages if you want to. And this is also using Spring Boot, available as a Spring Boot application because of Spring Cloud Stream. Okay, so wrapping up, so streams, they are a new type of data structure in RabbitMQ. They've been there for a couple of years now. They are good for large fanouts. You can go back in time, replay your messages. They are much faster than queues, so you can use RabbitMQ for high throughput scenarios. And you can also keep a large history of messages. You can easily use streams inside your Spring applications. So it starts with Spring MQP and Spring Rabbit. You can set it up very easily with Spring Boot, and you can go further with Spring Integration and Spring Cloud Stream. So yeah, you just have to enjoy them now. At the end of the presentation, there are some links to blog posts and documentation if you want to go further, and more links. And thank you. And I think we have a few minutes for questions. You can speak in the mic, if you, or I can repeat.
Question is it licensed or is it free, open source?
The question is whether it's commercial or free software. This is the same license as RabbitMQ, so this is free software, open source software, the server side and also the libraries. Another in the back.
Do you know how the throughput of SuperStream compare with Kafka?
So the question is, how does it compare to Kafka, especially for SuperStreams? No, we haven't tested exactly the two solutions. It's so much faster than queues that we focused a lot on performance, but I think that we usually we max out the hardware and the network, so it's as fast as we like it. I think, to be honest, I don't know, but it should be something similar for, but again, it depends on the tuning, on the use case. Another question? Yep.
So with AMQP, we kept the message size rather small. Do we have the same restriction here for message sizes?
So the question is, with AMQP, we should have reasonably small messages with AMQP. Do we have the same limitation with streams? Yes. No, not a gigabyte, please. So yeah, that's. There are constraints, like for example the max frame size. There are only guidelines, I would say. Okay, it should be reasonable. Why did you have like large messages or?
I was thinking about encrypting videos.
So the question is, if we can encrypt videos in streams, it's maybe too large for this kind of solution. Usually what we try to do is we try to have some kind of ID inside the message that points to some data store which is optimized for this kind of storage.
Is there any existing process for like shifting from AMQP to stream, like any documentation or something?
The question is there some documentation to how to switch from AMQP to streams? Not exactly. We have documentation on, for example, on how to use streams with AMQP. So this way, you can see I have an application. I'm using this API. Can I use the stream semantics with this API? Then we have a large documentation on using, for example, the Stream Java client, but not exactly a way to go from one to the other. These are different tools, so you don't have to migrate from them and from one to the other. Or maybe if you feel that one of your use cases is awkward with queues, maybe you can consider switching to streams, but there's no an obvious, it's not an evolution exactly, version 2. Okay, I think we are done. If you have any more questions, I'm available. And please take the survey. And let's stay connected. You can follow us on X and visit the website. And many thanks. Thank you for attending.